To look more into this idea of a generator, let's say we have a coil of N turns of wire with an area A, and we rotate it in this magnetic field, pointing to the right in this case. Now, we need a way to set up the ends of the wire into a circuit without winding them up into a big twisted mess and destroying them. So what we use is the setup that we saw when we looked at our commutator and brush from the electric motor. We have our loop, only one loop is shown here, but it could be arbitrarily many. And these legs scrape along these C-shaped pieces. So we've got brushes and commutators, and that's what we use to connect this spinning thing to something that's fixed. Anyway, this is going to work so well to make a generator because a generator and a motor are really the same thing. In one case, we let the mechanical effort turn it to produce electrical energy, but we can also let the electrical energy turn it and get mechanical work out of it. If we spin this coil here by hand or by steam power or whatever, we could charge a battery. Now, what's the EMF produced by the rotating coil? Again, it's negative N delta phi delta T. So we put in what phi is, negative N delta BA cosine theta delta T. Again, B and A are not changing, so they can come outside. And all that matters is the angle between the coil and the field. How is the cosine of that changing with time? Now, if the coil is rotating at a constant angular velocity, which is what we're going to work with, its position at any time, its value of theta, is just theta I plus omega t. We don't care where it started, so we can get rid of that. This means we have cosine of omega t is the thing we care about. Now, this is a result from calculus that you don't have to know, you're not supposed to know, but what you get out of that, if you do delta of cosine omega t over delta t, you'll pull out a factor of sine instead of cosine omega t, and then one factor of omega. So this is our actual formula for the voltage coming out of this rotating backwards motor, this electric generator. It depends on the number of loops, the strength of the field, the size of the loops, how fast you rotate it. This sinusoidal dependence, all this changes is, do we get a maximum, a minimum, zero? This is the time-dependent part. The rest of it is fixed for a given generator. So what would this look like? Well, if we had a fast recording voltmeter, and they actually exist and we call them oscilloscopes, if we connected the oscilloscope's leads to the end of a battery, we would just get something like this, 1.5 volts. And it would be straight and horizontal the whole way. It would only drop as the battery gradually died. On the other hand, if we connect these same voltmeter or oscilloscope leads to the generator, what we get is like this. So we go back and forth from 0 to a maximum voltage to 0 to a voltage driving current the other direction, back to 0. This goes on and on and on forever. We can't just plug the oscilloscope leads directly into the wall. You can do it with a voltmeter if you have it set on the right setting. But anyway, if we did that, if we set that up so it wouldn't kill the oscilloscope, we would get something that looked like this. And what we would notice is the top here, instead of 1, it would say it would be 170 volts, and the bottom would be negative 170. And this time here for one full cycle would be 1/60th of a second. In Europe, it would be 1/50th of a second. If instead of a regular wall outlet, we use the outlet that powers your dryer or your stove, we'd see instead of 170 up here, we go all the way up to 340. One of the side effects of Faraday's law is something called eddy currents. This is not a person's name. This is eddies like circular motion. So this is a place where the water's velocity field is curling around a little bit. When a conductor moves through a magnetic field, it sets up these circular currents, and they act like velocity-dependent friction, or air resistance. There's a really cool demonstration you can find online. We drop a magnet through a copper pipe. It takes much, much longer than it would take if we dropped a piece of wood through a copper pipe, or if we dropped the magnet through a plastic pipe of the same length. It takes very much longer, and the reason is, As the magnet falls, let's pretend the North Pole is pointing down, because something will be pointing down, either north or south. If the North Pole is pointing down, as it falls, you can imagine this copper pipe cut into a zillion little copper washers. And as this magnetic field approaches, we're getting magnetic field through this copper washer. The copper washer fights that by establishing a current the other way so that it pushes up against the North Pole. So it makes a North Pole that pushes on this one. As the magnet falls and this South Pole moves down, the net effect is decreasing the flux in such a way that the copper washers behind it make a magnet that has a North Pole on the bottom face, meaning it's pulling back on the South Pole. So as we drop this, we're creating a bunch of currents that act to try and keep this magnet from moving at all. If we have a thicker copper pipe, it's even more dramatic. We can slow it down a lot. This effect, this is called magnetic braking. It's used in a lot of things, in roller coasters, high-speed trains. It's the thing that makes a modern exercise bike harder to push when you increase the resistance. And we can use this idea a lot of different ways. We saw earlier that a device could be a motor or a generator, and this is what's going on in electric cars. One of the reasons they get such good mileage relative to gas cars. In a gas-powered car, when you step on the brake, all that gasoline that you use to get up to speed, that energy gets turned into heat and radiated away, and you don't have any use for it. But since there are motors at the wheels of an electric car, when you hit the brakes, they start working backwards as generators, and they start charging the battery. Now, of course, they don't replace all the energy you lost, but they replace some of it. The odd thing that people might not expect is not just that something could be a motor or a generator, but it can be both at the same time. So when you're using a motor, it's actually acting like a generator while you're using it as a motor. This EMF that the motor produces in use is called back EMF, since it works opposite to the direction that the applied EMF is trying to turn the motor. It fights the wall outlet. If you know this explains a few effects you've probably seen before. There's a little bit more to it than this, but we can consider a motor to just be a big coil of wire. If it has some resistance R, we can say if I have an external voltage source V, I'm going to get a current that's I equals V over R, Ohm's law. But since the back EMF created works in the other direction, once the motor is moving, the current's going to be reduced to V minus epsilon over R. For a generator, we know this is epsilon, NBA, omega, sine omega t. So this starts out, when it starts out from rest, omega is 0. It's not rotating. It's just like there's no air resistance when you first drop a ball. Depends on the velocity. This depends on the angular velocity. By the time the motor gets to operating speed, if it's not doing anything heavy, like if you're pointing a power drill or an electric saw or something in the air and just letting it spin around, that takes very little energy. So the EMF is not far off from the driving voltage. We can put in some numbers to see. Let's say your wall is providing 120 volts RMS, because it does. And let's say at no load, the back EMF is 110 volts. If the resistance of the coil wire inside the drill is 5 ohms, and this is ballpark, we get a current while it's running full speed of 120 minus 110 over 5, 2 amps, which isn't much current. Now, when the motor starts initially, omega is 0, so the back EMF is 0. So what's the current now? 120 minus 0 over 5 is 24 amps. This is huge comparatively. This would be enough to trip your household breakers for a regular outlet if it continued. But it only does this for maybe a second while the drill spins up to speed and starts producing back EMF. So when you have this suddenly large current being drawn out of your house's electrical system, you might notice the lights dimming. So if you see something like an air conditioner, vacuum cleaner cut on, sometimes the lights will dim for a second or two. This is also known as inrush current or startup current or surge current. There's all sorts of different names for it. If the circuit breakers in your electrical box tripped instantly most of them are probably 15 amps for wall outlets, and if they tripped instantly once you got to 15.1 amps, you'd never be able to use anything with an electric motor because startup would cause it to trip every time. You don't need them to work this way because what you're trying to do with the breakers is keep the wire in the house from catching on fire. And 1 second of high current, if it's only this high, is not going to cause them to start a fire. This also helps explain how you can kill a motor if you aren't careful. If we look at how we build a motor, we put lots and lots of turns of wire inside if we want a large torque. We want as many loops in as possible. There's two ways to do this. First, we don't use ordinary wire, which is the stuff on the left with the red plastic insulation. We use the stuff on the right. If you notice, it looks very thin. It doesn't look like it has any insulation at all. It's really just a thin layer of shellac that's painted on it. So it works as insulation, but it's not very thick. If we use this magnet wire, which is not magnetic itself, but it's what you would want to use to make an efficient magnetic field, if we use this wire, we can put lots of it in there. We've made our drill motor, and now you're using the drill. You start drilling through something really tough, or the drill bit is dull and it starts to bind up. When it slows down, the angular velocity slows down, so the back EMF slows down. That means the current, and therefore the power it uses, goes up. Let's say you just keep going. You keep pulling the trigger. It is almost completely stopped. We know that the wire is going to be carrying somewhere around 24 amps. That's going to generate a lot of heat, and the insulation on this is so thin that somewhere it's going to burn through. And now you're going to have a gap in your wire. You'll have it shorted out because of this I squared R heat buildup, and you'll need a new drill.